Enthalpy. We are going to define a new property, which is known as the enthalpy. And we're going to discuss why enthalpy is useful. We have here a cylinder of hot water, and we want to use this to do useful work, that is, to lift a weight. There are several different ways we could do this. The most obvious one is to use a cylinder filled with gas and to keep the weight on the piston. We can use the heat from the hot water to heat up the gas expands, and we lift the weight up. Over here we have used the internal energy, U of the water, to do work and to lift the weight. But there are other ways we could also do work. So for example, we could use the motion of the water. Over here we've put an outlet pipe at the bottom of the water cylinder, and then we let the water escape out of it. As it comes out, we can use the momentum of the water to turn a wheel. And as the wheel rotates, we can use that to do useful work. Now, if we want to increase the amount of work that the water does, we can keep a weight on top of the piston. This increases the pressure of the water, and now when it comes out, it'll come out with a higher velocity, and the wheel will turn faster. The work done by the wheel increases. So what property of the water could we use to tell us how much work it can do? Certainly the internal energy of the water is important, but we just saw that the pressure is also important. So we would like to define a new property that includes both the internal energy and the pressure, and use this to tell us how much work the fluid can do. But before we can define this property, we have to answer another question, which is that how much energy did the fluid carry out when it emerged from the control volume? To calculate this, we need to know the flow work, which is the work done to push the fluid out of the control volume. If we assume that the pressure at the outlet of the control volume is P, and the cross-sectional area of the outlet pipe is A, then when we force a fluid element out of the control volume, which has mass m and volume v, and which travels out a distance L, we can then calculate the force required to push the fluid element out of the control volume. So F would be P, the pressure, times A, the cross-sectional area. The work done in pushing out this fluid element, which is the flow work, is going to be the force times the distance, F times L. Now F is equal to PA, so substituting that, we get PAL. AL is simply the volume of the fluid. So we can write that as being PV, where V is the volume of the fluid element which has come out of the control volume. The work done to push the fluid out of the control volume is P times V. But this energy is carried out by the fluid as it leaves the control volume. So the energy transported by the fluid as it leaves the control volumes includes both the internal energy and the flow work. So that is U plus PV. We are going to define a new property which we'll call the enthalpy. We'll give it the symbol H, and this is equal to U plus PV. The enthalpy is an extensive property because both U and V are extensive properties. Enthalpy has the same units as U, which is joules or kilojoules. So enthalpy is very closely related to energy, and in fact that's why we select that name, because it sounds quite a bit like energy. We can also define a corresponding intensive property, which is the specific enthalpy. We give that the symbol the lowercase h, and that is equal to the enthalpy divided by the mass of the system. This equals U upon m plus P V upon m. So we can write H as being U plus PV. And the intensive property, the specific enthalpy, has units of kilojoules per kg. So why have we defined enthalpy? Enthalpy measures the capacity of a fluid to do work. Now, enthalpy is not a fundamental property in the same way that energy was, because it is defined as a function of other properties. So we define enthalpy because it is useful. And we will see this, especially when we get into the analysis of controlled volumes, that it becomes very useful to use the enthalpy because we don't have to keep track of the flow work separately. It is included in the enthalpy. Enthalpy is also useful in other systems, such as systems at constant pressure. Here we've got a gas in a cylinder, and we are going to heat this at constant pressure. So the gas expands as we heat it, and it does work on the surroundings. We want to know how much heat was added to the system. We can show the process on a PV diagram, and the process is a horizontal line. The work done is minus integral of P dV. P is a constant, so we can take it outside the integral. And then if we integrate, we get that the work done is minus P, V2 minus V1. Now we want to take the pressure inside the brackets, and we'll write it as minus P2V2 minus P1V1. So in the first term, we've written the pressure as P2. In the second term, we've written it as P1. And we can do this because P1 is equal to P2. And we'll see in a minute as to why we write it this way. So now coming back to our original question, how much heat was added to the gas as it expanded? We can write an energy balance using our first law, that the work plus the heat is equal to the change in internal energy of the system. Now we have just calculated the work done by the gas as being equal to minus P2V2 minus P1V1. Let's take this and substitute it back into our first law. If we solve for the heat, Q12, that is equal to U2 minus U1 plus P2V2 minus P1V1. Let's gather together all the properties at state 2 and all the properties at state 1. And we'll write it as U2 plus P2V2 minus U1 plus P1V1. Now we should recognize immediately that these are just the enthalpies, H2 and H1. So Q12 is equal to H2 minus H1. And this is a very important observation, that the heat supplied to a constant pressure system equals its change in enthalpy. To summarize, we have defined a new property enthalpy, and we have defined it as H is equal to U plus PV. Enthalpy is an extensive property and has units of energy. Enthalpy includes both the internal energy and the flow work. The enthalpy measures the capacity of a fluid to do work. We have also defined the specific enthalpy, and the heat transfer to a constant pressure system equals the change in enthalpy.